In this workshop, we will create a typical scene for a TV commercial. The goal is to create a turbulent interaction of fruits falling into milk. All this happens in slow motion. For the fruits, we will use 3D models of blueberries. The berries should be driven by rigid body dynamics to achieve a realistic interaction with the fluid. The biggest challenge with this project is to achieve the typical behavior of milk. Milk has specific properties. It is as liquid as water. This means that milk has a very low viscosity. On the other hand, milk forms out drops and coherent splashes due to its high surface tension. When you have a close look at milk, it also seems to react slower than water. This is also a result of high surface tension. To create the fluid's turbulences, we will use a combination of different emitter types and initial states. Before we start the fluid simulation, we need the models of the blueberries to simulate their motion and place of impact. The blueberries are stored in RealFlow's native SD format and can be imported with the Control and I keys on your keyboard. You can see that the three objects are aligned and that they have to be repositioned. This can be done with the object's SD to curve button. When you click on this button, the objects will be unlocked and they can be positioned, scaled and rotated with appropriate tools from the icon bar. The next object is a container to enclose the berries and fluid. This will be our simulation environment and it should not be too small. We add a RealFlow cube and scale it to 10, 4 and 6. Please be careful with these values because they depend on your current axis setup. With the Preferences window, it is possible to adjust RealFlow to virtually any software because some programs use the Z-axis as the software's height axis. Others use the Y-axis. You can change this in the Preferences panel under General. In this workshop, the Y-axis is used, but if your setup is ZXY, the scale values are 10, 6 and 4. In relation to the container, the blueberries seem to be too big, and therefore we have to scale them down. A value of 0.5 appears to be reasonable. The berries should come from outside the surrounding box and fall into the fluid. The impact should happen near the cube's center or a little earlier. The blueberries can be easily shifted to their initial positions with the Move tool. The dynamic parameters for the desired motion can already be adjusted, and for this purpose it is necessary to activate the blueberry node's active rigid body feature. With the Shift key, it is possible to select more than one node and apply the option for all objects at once. Now you can see a panel called Rigid Body. Mass is a very important parameter because it strongly influences the strength and height of the splashes. Depending on your 3D software and scale, the default mass can be very high. Values between 150 and 300 should be sufficient. Another parameter that has strong impact on the fluid-body interaction is velocity. Even very small objects can cause huge splashes when they are fast enough. For our commercial, we need rather moderate splashes because we do not want to see a torn look with lots of fine drops. Since a body's mass does not influence its acceleration, it is enough to adjust the initial velocity of the motion path. To make everything a little more interesting, the initial velocities should not be exactly the same, and we can also add a height component. A high object friction parameter will prevent the blueberries from rolling away too far. Later, the fluid will slow down their motion as well. For our tests, we need a few more things. The first one is a gravity daemon. We can leave its default value of 9.8. Then we have to enable the interaction between the blueberries and the container. Since the container should not move, we activate passive rigid body and change collision side to inside. This is necessary because otherwise the berries would simply bounce off the walls. You most probably have to perform a couple of test simulations until you have found the working settings. The previously made settings are the result of several tests. This is the motion path of the objects. What we need now is milk. For this test, we create two collapsing piles of particles from square emitters. When they collide, they will create a turbulent splash, and this is a very effective way to check whether our settings create a milky look or not. Place the emitters to the left and right ends of the container and scale them until the scene looks roughly like this. Since we do not need the blueberries for the first fluid test, we can make them inactive. By default, emitters create a constant stream of particles. The velocity is controlled with the speed parameter. It is also possible to create defined volume. To enable this option, set speed to 0.0 and volume to a value around 2.5 or 3. The final height depends on the emitter's distance to the cube's ground, and you can check it with the reset button. We also have to adjust the second emitter exactly the same way. When you select both emitters, you can see the current number of particles in the viewport. This information is very important because it directly affects simulation time and quality. Finally, we add some randomness with V and H random. Now, select both emitters and open the Particles panel. To get a better impression, the emitter's resolution should be increased a little here. Values around 5 are good for a first look. The next parameter is density. A fluid's density strongly depends on its composition. Pure water has a density of 1,000 kilograms per cubic meter. Milk, on the other hand, is a blend of water and tiny drops of fat, a so-called emulsion. A density value of around 1,200 should be okay here. The higher density value will also help to create a more sluggish look. The internal and external pressure parameters have a strong influence on fluids. The internal pressure is a fluid's tendency to expand, and the external pressure can be seen as the counteracting force. In our case, internal pressure should be decreased, for example, to 0.5. Viscosity is another very important property. No other parameter has such an impact on a fluid's behavior, and with viscosity you can create almost everything from alcohol to honey or tar. As already said, milk is very similar to water, and therefore the viscosity value should not be greater than 6. 5 is even better. The last parameter is called surface tension, and much better suited for our purposes. With higher values, the fluid's tendency to form drops and filaments increases, and this is exactly what we need. To get really nice drops, the value shouldn't be too small, and we try 200 here. Now, it is time for a first test simulation. Open the Simulation Options panel and enter 200 for maximum substeps. Substeps can be seen as a quality level for a simulation, but normally we can easily work with a much smaller number. Values between 150 and 200 will work. Some fluid artists even use only 50 or 75 substeps for previews. As you can see, the fluid forms nice drops. There are also splashes, but the fluid does not break apart into tiny droplets. We also have a smooth surface, and our virtual milk has the right velocity, not too fast, not too slow. All in all, we can use the adjusted parameters, but you can also experiment with other settings, for example, higher surface tension. When you have a look at the fluid simulation, you will recognize that we don't have enough particles. So far, we've only created a shallow puddle, and that is not enough for a nice fluid object interaction. With a fill object emitter, it is easy to control the amount of particles, and this is another advantage, we can introduce more turbulences. Add a fill object emitter and link the fluid container to it. Set fill volume to yes and click on reset. Of course, we do not need a completely filled object, and therefore the fill ratio must be changed. Please mind your axis set up here as well. Here we have to decrease fill Y ratio. A value between 0.1 and 0.2 should produce a sufficient amount of particles. To get more randomness, jittering is set to 0.2. When the particles of the square emitters interpenetrate the fill object emitter, it is necessary to change the square's volume parameter or move them to a higher position. The emitter's physical properties have to be identical with the square's emitters because we do not want to create two different types of fluids. Open the Particles panel and make the appropriate settings. Only resolution can be different, and for the first test, a value of 5 is sufficient. The final setup should look like this. The fluids collapse, interact with each other, create nice splashes, and we also have enough particles. What we need now is a high-resolution simulation and an initial state. To create more particles, the emitter's resolution must be increased. The values do not necessarily have to be identical, and you can use different settings for each emitter. Since resolution will directly influence simulation time, it is important to know the final number of particles. The statistics panel shows this number for each emitter under existent particles. After a change of resolution, we have to reset in order to update the statistics panel. You can also see the number of particles in the viewport. With resolution values of 10 for the square emitters and 15 for the fill object, we can create approximately 750,000 particles. This is good enough for a simulation and a clean mesh. To avoid escaping particles, a K-volume daemon is added and adapted to the fluid container. We reset the scene and start the simulation. We can see that the fluid is very turbulent at the beginning, but quickly settles. For the final simulation, we need more splashes and motion to create the turbulent impression. We will use a daemon for this, but a little later. Now we pick a particular frame and define it as an initial state. With a few settings, RealFlow will start the next simulation from exactly this point in time. For our initial state, the fluid should already have settled a little. Frames between 75 and 100 seem to have the desired properties. To create the initial state, select all emitters and set Use Initial State to Yes, then click on Make Initial State. To finally activate this function, choose Reset to Initial State. When you reset, you will see that the first frame is exactly the one we have just specified. To get more turbulence into the system, we add a wind daemon. A wind daemon is very versatile and perfectly suited for our project. To create the desired effect, change Bounded to Yes and adjust the radius value to get a vase-like shape. The idea is to blow some wind from beneath into the fluid. To get a random look, the daemon's position and strength will be animated, supported by a moderate amount of noise. To change wind direction, the daemon has to be rotated around 180 degrees until the arrowhead points upwards. Now, shift the daemon along the height axis. It should roughly be in the position you see here. Create a keyframe for frame 0, then shift the timeline slider to the next frame. Create a new set of keys and repeat this process until you have reached the last frame. Currently, the wind will blow with constant strength, and we have to change this. Go to the Strength parameter, right-click on it, and select Open Curve. We want phases of maximum strength, but also times without wind at all, and expression is perfectly suited to achieve this behavior. A simple sine function is used with time as a variable. This means that RealFlow calculates the sine for the current time, t. The wind should range between 0 and 12. To achieve this, a factor of 6 is multiplied. Now the range is between -6 and 6, and we need an offset. Simply add 6 to the function's end, and now the values are running from 0 to 12. When we take a closer look at the curve, we can see that there are hardly any peaks. In our scene, we need more of these ups and downs to create a vivid motion. This can be done by multiplying the time variable with a factor greater than 1. You can see that the spikes become denser with higher values. Here, we are using a factor of 15. Please bear in mind that the used values are the result of several experiments and test simulations. When you have to create a fluid shot someday, these tests are essential and they need, of course, a certain amount of time. Previews will help you to evaluate the fluid's motion, so you should always use them. Since the wind daemon should only affect the fluid, not the blue breeze, we have to remove it from the Global Links window and link it to the emitters under Exclusive Links. Only a few more steps and the simulation can start. First of all, make the blueberry nodes active again. Then, we have to activate the slow motion effect. Open the Simulation Options panel and enter 75 for FPS output. Now we can also decrease the number of maximum substeps because we do not need such a high precision anymore. A value of 100 is good enough. Close the window, save the scene, reset, and hit Simulate. Due to the rather large substeps, the simulation performs very fast and should be finished after 1 or 2 hours. This, of course, depends on your computer. Create a preview to evaluate the simulation and adjust the parameters if necessary. In this case, you have to reset and resimulate again. The fluid behaves exactly as desired. There is enough turbulence, the splashes are not too high, and the fluid particles stick together. We can see a few drops, but the fluid is not totally torn. The last part is the creation of a mesh that can be shared and rendered in a 3D program. RealFlow provides 3 different types, and here we will use the RK mesh. Add an empty mesh container and right-click on it. To attach the emitters, choose Insert All Emitters. A mesh engine creates spheres with a certain radius around the particles and blends them together. The number of polygons determines the resolution of these spheres and finally the level of detail. Therefore, the mesh parameters are subdivided into 2 areas. In the first section, we can define the polygons and the look of the mesh. Polygon size is the mesh's resolution. Lower values will create more polygons. A good value for many cases is around 0.04. The other values can be left untouched at the moment. The second section becomes visible when we click on an emitter. There you can find the radius value. As a starting point, radius and polygon size can be the same. If you need more detail, decrease polygon size. If you need thicker fluid borders, increase radius. Please note that the emitter-specific parameters can only be changed individually. Multi-selections do not work. A mesh can be manually created from any frame. Simply move the slider to the desired position, right-click on the mesh container and choose Build. The mesh appears in the viewport, and you can change RealFlow's shading mode to get a smoother look. At the moment, there are not enough details, so we alter polygon size to 0.025 and build the mesh again. The result already looks very nice. The fluid borders should not be so rounded. Instead of changing radius, we will filter the mesh. The filter option must be set to Yes. Relaxation is the parameter of interest, but we leave the default value. Instead, steps is decreased to a value between 5 and 20. Here, 8 is used to achieve a moderate effect. The more steps, the stronger the filter effect. Now, the mesh fulfills our expectations and we can try the settings with a few more frames. When the results are satisfying, the entire mesh range can be created. Rewind the timeline slider and click on the Create Mesh button. Once RealFlow has finished its task, you should create a new preview, evaluate the mesh, or import it to your 3D program and render it.